Now you're at 100 meters. Now let me ask you, what is going to be the conversion? The SD, or in this case, the pressure, or what? 100 meters. Oh, yeah.
But you can find it kilograms.
Okay, and you write a equation. I like it. Be careful with the units. I like the CSV. How's that going, guys? Any question or? So remember, the only thing here to change is that the value of porosity and the value of the density. Raise your hand. Bulk density, yes. So you see how the bulk density has
Units per gravity again. Meters per second squared. That would help.
Oh, does she want just the gradient, so in terms of Z? Yeah, he wants a gradient.
Yes, the density times gravity.
Yeah, so he doesn't care. He wants it in specific units.
What do you get for the
Pounds per gallon, PSI.
For the
I hate this
you
unit.
get 2.6. I did this. 2.8. Yeah, and then kind of the 1 minus the porosity. What did you get here?
2.52 kilograms per centimeter cubed. 2.808 kilograms per centimeter cubed.
Let me read
Did you use the ones from our homework? No, I used the one from the website you told us to use. Yeah. It's the Cranes. It's not on there. He just posted it up there on the CR8INS. Petrophysical.
Okay, yeah, I got it.
Pen,
You know what the final
Yeah.
Can I just take the number from you?
Yeah. Oh, it's just 2.85 and 2.71.
5.
Yeah. I hate doing unit conversions.
What? Yeah, but it's click ask. Oh, it's not what you but it should be the one over there. But is that like a how did you convert? So that's rare for CC, right?
Yeah, cubic centimeter. So I had to convert.
You said kilograms. What was it?
Isn't it just grams?
25,000
grams or kilograms?
It's grams. That's Pascal for me. This is not
Yeah,
gonna.
Pascal.
And then 25.8. And it's not 2 kilograms per cubic centimeter. Cubic centimeter. That's this big. Yeah, that's
This unit conversion.
what unit conversion do you do?
A lot. Are you done?
Are you trying to convert this to that?
All right, guys.
No.
Let me tell you more or less the answer, okay? I think you know how to solve this problem, and you're very close to solve it. So basically, here you have to compute the density with that equation that we saw before. Then the gradient is just going to be the density bulk times G, and that's going to be more or less 26 MPa. it's going to be more or less 26 MPa per kilometer. Check your results. It's going to be more or less 1.1, let's say 1.15 psi per foot. And is it going to be more or less, how many pounds per gallon? 22 pounds per gallon. We didn't talk much about the pounds per gallon before, but remember that a density or a gradient of 0.44 psi per foot, which is given by the density of water, it's equal to a gradient of 8.3 pounds per gallon, ppg. Okay, so continue working in the problem. I strongly recommend that you check the solved exercise and if you get stuck at some point. So, let's go to problem number 2, okay? Problem number 2. Okay, problem number 2 is just a reminder that how to solve an integral with a trapezoidal rule. That's it, okay? That's what you should remember in order to do the other problems with the numerical integration. The numerical integration is just an extension of the trapezoidal rule. So here in problem number 2, you have a place offshore. And apparently, let me draw first this over here, and then I'm going to switch. It's offshore. You want to know conditions at 10,000 feet of depth, total depth. Remember, I'm always going to refer to depth from the sea level, and you have 1,000 feet to get to the sea floor, and then 10,000 feet to get to this point. And here's where it becomes a little bit different. You know that the density of the water is, where's the density of the water? Okay, it doesn't say, so we're going to assume it. Whenever it doesn't say, just make a fair assumption. I expect that also you know some typical numbers like lithostatic gradient, hydrostatic pressure gradient on top of your head, okay? So what is the density of water? What would be more or less a good assumption? Yeah, okay. So when we calculate these gradients, I prefer to go with a metric system. And the very easy number is 1,000 kilograms per meter cubed. And
Professor?
yes.
I can't see what you're like.
Yes, I know. Just 1 second. I will copy these numbers, and then we'll show what I'm doing in here. Just
I was going to ask, it says water depth is 1,000 meters and we're 10,000 feet.
correct. I fell in my own trap, you see. Be very careful with the units, okay? I like to mix the units because you need to know both systems. I don't know where you're going to end up working, but if you work outside the US, you will see many places you need to know how to work with the metric system. So 1,000 meters and 10,000 feet, which is about 3,000 meters of depth, right? Just wait a second for that, and then I want to put the densities here. Okay. This is what we have in the problem. We have a depth of 1,000 meters to the seafloor. Then we have 10,000 feet to the point that we want to compute stress. 10,000 feet is going to be equal to 3,054 meters. Okay? And then the problem says that from the seafloor to 500 meters below the seafloor, the bulk density is not constant but increases linearly from 1800 to 2350. This variation is taking into account the fact that rocks and sediments compress as they go deeper. So the question now is, what is the value of SV at this location? When we use the equation with a constant density, we just did this density times CW times, if we had a constant density, the constant density times this length, right? And if you notice, that is just the area under this line. It's an integral. That is what the equation told us, that the general solution is just an integral. So if you want to compute the stress, in this case, you just have to compute the area of this of the line from here to the axis. So how would you go by that? You multiply this length times this constant density plus, how would you compute the area of this trapezoid?
Break it into rectangle and triangle.
You could do that, but the easiest way would be just take the average of these two and multiply times this length. So the average of these two numbers is going to give you a rectangle that gives you an area which is equal to the area of the trapezoid. Plus this density times this other length, and that's it. That's the value of the vertical stress. Okay? So compute a number and let's see what you get. Here Muhammad tells me that my memory is failing, that this is not 54 but it's 48. And I think he's right. So 3048. I was off by 6 meters. And this is the exact same thing that you're gonna do in Excel in the next exercise. Okay? So if you get the answer, please let me know, and I'll give you some extra points. Okay?
The depth between 1800 and 2350 is 500 meters, right?
Mm-hmm. Isn't it 550?
Between what?
The 1800 row and 2300 or 2350.
Yeah, it's 500. That's what it says in the problem, right? I think I read that correctly. Yeah, it says increasing linearly 500 meters below the seafloor. Yes. Yeah, you have to multiply to get the actual circle. forget the G, okay? Anyone has the answer?
We are measuring the SB, the entire thing, right?
Yes. I want to get SB at this point of it. Yes, you have the answer?
I think so.
What is the answer?
Really big.
No, but give me a value in MPa, okay? Because you could give it in Pascal, but try always to convert those stresses either to MPa or to PSI.
I don't think it's right, but it's 5.56 times 10 to the 4th.
No, I don't think so. No. The determinant.
1,470.
What?
Oh, sorry, 10,470.
10,000 MPa? I don't think so. I don't think so. As a general rule, guys, remember all these stresses and pressures are going to be in the range of less than 20,000 psi and less than 100 MPa. If you get more than that, it's very likely it's wrong. Remember the G, okay, and remember the units. You have the answer?
I have 8,068 psi.
8,068 psi. That sounds reasonable. What about in MPa?
I have
55.6. Okay. Another very useful conversion, guys. 3,000 psi is equal to 20.6 MPa, or that's a number I remember a lot because I used to conduct